In this notebook, we're looking at memory and context engineering techniques for AI agents. We're going to build with Oracle AI database, which is that memory core. We're going to use LangChain and Tavily. We're also going to use OpenAI for the actual LLM of the agent itself. We're going to use the Oracle AI database available within the LangChain library. Then we're going to start going deep and looking into some memory engineering techniques and looking into what agent memory is. We're also going to look at context engineering techniques. Then we're going to give our agent access to the internet to get additional context that we can store into the memory. Then we're going to look at an agent loop and actually execute the agent. We're not going to use any frameworks or abstractions, so we can see how our context window is actually getting generated. This is going to be fun. We're going to run through some of the cell and learn a lot. When I was making this notebook, I started to realize that the first job to be done when we're building this system is memory engineering, because we have to think about how we model different memory types. So that's data modeling. Then context engineering might come second. Prompt engineering is usually within context engineering techniques and also within the agent loop itself and in some aspect of memory engineering. Memory engineering is usually the extensive aspect of the job to be done when we're building AI agents for production that are reliable, believable, and capable. So let's go through this notebook. We are going to look at 5 different types of agent memory. We're going to look at conversational, which is the interaction between the assistant and the user. We're going to store that in a SQL table. We're going to have the knowledge base, which is documents and facts about the problem domain. We're going to store that in a vector store. With Oracle AI database, you can actually store embeddings and different types of data in one single database. Then we're going to look at workflow memory, toolbox, entity, and summary memory. Remember, you can take a context window, summarize it, and store that in our database. The compression is a context engineering technique called context compaction or reduction. We're going to see these in action, and it's actually quite simple here. We're going to cover just-in-time retrieval, dynamic tool calling, which is a way where we can scale the tools that are available to an LLM. We're going to look at entity extraction as well. LLMs and agents usually interact with different types of entity, whether artificial or biological, like me and you. It's always good to have a record of different entities in case we encounter them again. You need to have an OpenAI API key, and we're going to be using a local installation of Oracle AI database. All of this is the actual memory core of your AI agent locally. And by the end of this, you're going to be able to understand what we mean by memory layer or memory manager. I prefer the term memory manager better than memory layer. So let's go with installing some of the libraries here. We're going to be using the LangChain Oracle DB integration. We're going to be getting some embedding models from Hugging Face as well with the Transformers library. We're going to be using LangChain OpenAI and Tavily. We're going to run this particular cell to have all the libraries installed. We're going to get our Oracle AI database working locally. I'm just going to open my terminal here, and we could run this Docker command, just copy and paste it. Let's minimize this. Now we can start to set up the Oracle AI database. And this function will actually have it has a waiting procedure just to make sure the Oracle database is actually running. And we're going to create our vector user, and now our database is ready for us to get started with it. There's troubleshooting information that can help you get started with Oracle AI databases, both in this notebook and online. Now we can connect to the Oracle AI database. It's got a bunch of retry mechanism, and it's going to make sure everything is all configured. Now, here's what we're going to do. We're going to create a connection to the Oracle AI database and store that within our development environment. If this works properly, you should see the version of Oracle AI database that you're using, but also you should see the specific banner that you're using, the Oracle AI database 26 AI. That is your setup complete. Now we can use the Oracle integration within LangChain. This abstracts away some of the setup for creating your vector stores for all your memory types. In this section, we're going to generate embeddings for data that we pass into our vector store. We're actually going to create our indexes. We're going to add documents, see examples of queries and filtering using Oracle AI database. Using LangChain, we're going to get the Oracle vector store module, import that into our environment. We're going to use Hugging Face embeddings, create index functionality to create vector store indexes. We're going to use the equilibrium distance as a distance strategy to calculate the distance between 2 or more vectors. In this cell, we're bringing in a Hugging face embeddings, particularly this paraphrase MPNet embedding. I just chose a random one, but you can actually use different embeddings from Hugging Face for this specific notebook. Over here, we use the Oracle vector store integration from LangChain. We pass in that vector connection that we initialized earlier on. We pass in our embedding function, which is going to take in this embedding model particularly, and we pass in a name for our vector store. We're just going to call it a vector search demo. This is the table name. We pass in the distance strategy. So this is just an example, just trying to show you how we can create a table where you can store vector data within Oracle AI database. So once that's run, we can create our vector index as well. We're using this create index function from the LangChain Oracle integration. We pass in our connection. We also pass in the vector store. This is going to come from the actual arguments of the function. We're going to be using an inverted file vector index for this particular vector store. There are other indexes you can use. I'll probably go through some of them in future videos. We're going to use the function we just created to create our index. This vector index allows for the efficient retrieval of vector information. Let's ingest an example data. We're going to ingest this text. A table space can be online or offline. It's just random text. And we're going to pass in some metadata with this text as well. Then we call the add text method on the vector store we initialize. We're going to pass the text variable, and for metadatas, we're going to pass in the metadata. Now we have items in our actual AI database. What can we do? Now we can actually query the vector store using very simple natural language. We're going to pass in this query. How does Oracle handle table spaces? We're going to get documents that match the query in terms of semantic similarity. The documents returned should match this query in terms of semantic similarity. So we can see there are two results returned from what we ingested. This is a semantic search powered by vector search. We can see what the score with this similarity search is. The reason why you might want to score is because sometimes you want to add a threshold to see if you have a certain similarity. You want to take certain records that have a similarity score and discard others. You can do this with the integration where you can have a similarity score as well. In future videos, we'll go deep into different type of vector indexes and what the score actually mean and how we can modify it as well and optimize it. Now we can do some filtering. We only want to retrieve records that match this filter. Filter is within the link metadata, it needs to be equal to document example test 1. So we only want to see records that have in the link attributes, the metadata, document example test 1. That is exactly what gets returned. We get that exact record from our table. There is more filtering that reduces the scope of the search and I filter the results. We can explore more of this and the documentation will be made available as well. Let's go into memory engineering and agent memory. So we understand what agent memory is, which includes the embedding model, an external memory store, the context window and the LLM, and a memory management system that goes on top of this to move data between these components of your agentic system. Then you have memory engineering, which is what this session is focusing on. It's the code, it's the scaffold, and it's a harness that we build in our system to move data through the components we just identified. We're going to generate some synthetic data as well. We're going to do a bunch of pre-filtering and retrieval optimization within memory engineering. The key thing is we're going to build this memory manager within this section as well. Memory engineering matters because we need to make AI agents more reliable. We need to make them believable, which means we need to feel like we're interacting with an intelligent entity whenever we're using our system. Then we need to make it capable, which means they can actually do certain tasks with robust additional skills. Without memory, agents are going to forget. Your agent is not going to remember the users of your application. They might repeat mistake. They might actually just not have any context required for a specific task. But when you implement proper memory engineering techniques, you're able to build agents that adapt and evolve with more interactions. I try to show this using 5 memory types that we can see in agents today that are very useful. So those are what we're going to cover in this section. The memory types we're going to cover are conversational, knowledge-based, which is semantic memory, workflow, toolbox are type of procedural memory, entity is a type of semantic memory, summary table is a type of episodic memory as well. So is conversational memory, that's a type of episodic memory. if you put timestamps in summaries, don't they become episodic? So in this code, for each memory type, we're going to create its dedicated table where we're going to store different rows that correspond to memory units for each of these memory types. In this cell, we're going to create individual tables. You can store vector data, and you can see we're going to use that vector connection we created earlier to create the tables. This also drops any existing table because we want to start fresh. Now, part of context engineering is to understand the context window limits of the LLM you're using, passing in some of the context window limits for the particular LLMs we're using. This is like a lookup for the context window utilization engineering that we're going to implement over here. Conversational memory is just going to be a very simple table. There's not going to be any semantic retrieval being done here. We're using a SQL query to create a table, and we're setting all the particular attributes. We're going to have an ID or session ID as well if you want. The role could be either assistant or user. Then we're going to have the content of the actual conversation either by the user or generated by the LLM, a timestamp, and created at timestamp. To be honest, we can probably remove one of this timestamp. Then we're going to have a summary ID. The reason why we have a summary ID here is we want our actual summaries to be able to be uncompressed as well. Whenever we want to compress summary, we can look at the summary IDs that correspond to it in the conversational and any other form of memory. We create indexes to enable efficient retrieval and then run this function by passing in the conversational table name and the connection to our database. When this is done, we should have our table. It's done. Very quick and very easy. In the next section, we're going to use our LangChain integration to create the vector stores that we need for the other types of memory that we require semantic search functionality for. This will be the knowledge base, workflow, toolbox, entity, and summary memory. And this code is just going to use the Oracle vector store integration with LangChain, pass in the embedding function we want to use. We're also going to pass in the specific unique table name for this specific vector store. So here we're actually going to create individual index for each of this so we can conduct semantic search using vector search capabilities. So all the index have been created. When you're implementing AI agents, you can give them access to tools. You can give them access to tools that they can call themselves, or you can make the tool call the actual method programmatic, and the agent doesn't have any decision as to when to call this or not. It just happens. When you want to read from conversational history, that isn't agentic, that is programmatic. When you want to read from knowledge base, you can make this agentic, but I'm making it programmatic. It's going to happen every time in an execution within the agent loop itself. Then read and workflow, again, programmatic. In fact, most things here are programmatic calls to the memory as opposed to agentic. The only thing that is agentic here is the ability for the agent to actually search the internet, the ability for the agent to do just-in-time retrieval to expand on a summary, or to even just decide to summarize and store. So that is something here that is just agentic. So summarize and store means that the agent can actually, when it sees the context window get into a certain threshold, it has the ability to summarize the context window and store it in the database. So that's what we do here. Sometimes you can make everything programmatic. It depends on your use case. So one thing is retrieval operation are what you want to do at the start of the actual agent loop itself, because you need context. Whenever information goes into the context window, it becomes context, right? Wherever memory comes in, memory becomes context when it comes into the boundary of the context window. So the agent can't know what it doesn't know. So we have to always do some form of retrieval at the beginning, and then there's consistency as well. I just kept some writings around this agentic versus programmatic uses of tools and why you may use one or the other. So let's talk about the memory manager. I think memory manager is the right way to think about these classes of tools that help you manage memory in an agentic system, as opposed to memory layer. This notebook is educational, and you can tell because we have write and read for each type, but sometimes you might want to delete some items within each of the memory stores as well, not just read and write. But for demonstrative and educational purpose, I'm just showing like read and write functionalities, and you can extrapolate how you would implement some of the delete and update functionalities as well. We're going to have a thread ID. There's some logic in terms of workflow memory. We're only considering workflow memories that have greater than 0 steps. There are some frameworks there that some people might use. LangChain memory, but also LangMem is another library from LangChain that focuses on memory management. Mem0 is slightly popular. One of the pros is you begin to understand a lot about memory management. You begin to understand a lot about memory engineering itself and where to apply different engineering techniques. For example, when you use some tools that abstract away some of the retrieval strategies that you need, you don't understand how they're retrieving information from whatever database they're using or external memory store. Sometimes you might want to use graph traversal. Sometimes you might want to use vector search similarity, and you want full control over the retrieval strategies that you're using. In fact, you might want full control over some of the augmentation methods that you're using. But you might want to use a framework to move things faster, or create some MVPs or POCs, or just reduce the amount of code you have to write and maintain. There are pros and cons. It depends on what type of system you're building. Implementing different memory managers and going into memory engineering is the job to be done. And I think everyone should be able to understand it to some certain level. And most of these libraries are open source as well, so you can see some of the logic behind the code. We're going to go through the code of the memory manager. There are 5 types of memory: conversational, knowledge, workflow, toolbox, entity. There's also summary memory. That's another type of memory. I'm going to update the notebook to reflect this as well. We actually have 1, 2, 3, 4, 5, 6 type of memory. That's a lot of memory. So in this class, memory manager class is very simple. It's going to contain all the operations for our memory stores that we've just created, right? It's going to only the read and write operations. For writing to conversational memory, we're going to pass in the content, the role, the thread ID. Now, there's a bit of data modeling that goes into understanding what attributes you want within each of the memory types. We can cover that in future videos. Here you can see we're just executing a very simple SQL statement where we're inserting the actual information into the appropriate columns that correspond to the attributes that we actually passing in from the memory unit. And then we commit this transaction and we have the record ID returned from the function. You can read from memory using a thread ID, and we can just get the last 10 conversation. And one thing we actually do is, and this is where a bit of prompt engineering starts to come into memory engineering. It actually happens very early on. When we're reading our conversational memory, I'm adding a bit of prompt or instructions to the LLM on how to use the conversation memory. And you might notice that I'm putting in some hashes. This is context engineering in a sense, right? One of the context engineering principles you will see out there is to work within the constraints of your LLMs. One of the constraints of LLMs is that they were trained with a lot of internet data. Internet data contains information that has some form of hierarchical structure. For example, HTML has some structure in terms of information. If you're a web developer, you know about different HTML tags. You can have the body, then the head, and different tags that represent different organization of information. But you can also have Markdown. There are loads of Markdown information on the internet, and LLMs have been trained with this data, and they understand Markdown as well. Here you can see this is a bit of context engineering with some prompt engineering to give the information of how to use this particular memory store for the LLM to achieve a certain task. So here I'm giving instruction on how to use the conversational memory. With this instruction hierarchy, the LLM should be able to understand what instruction on how to use corresponds to what memory. We do this for all of the different types of memory. There are functions such as marker summarize, context compaction or reduction, summary where you take an extensive context window and summarize it. The trick here is to do it without any major information loss. Here, this function, we just mark some memory units to summarize. Then we can write and read from the knowledge base, and you can see the instructions when we're reading. This goes into the context window we're going to see later. Workflow memory, whenever we're doing a tool call and executing multi-step processes, we capture the specific query, the steps we've taken, and the final answer if it was a success or failure. This is procedural memory and experience for our AI agents. because whether something was successful or a failure, that is information we can pull into the context window of an LLM to replicate success or avoid failure modes. So what I do is whenever I store items into the workflow memory, in the steps, I actually store the function call on the arguments we pass in, and we see if it was a success or failure. If it was a failure, in the current execution, I would expect it not to follow the failure steps and try to explore a different path. So now we also instruct it on how to use this type of memory whenever we read from it. And the same pattern happens over and over again. We have this read from Toolbox and write from Toolbox as well. I'm going to talk about the Toolbox a bit later, because Toolbox is a very crucial technique you can use to scale your agents. Entity memory, we have this overlap of prompt engineering and memory engineering. I'm using GPT-4 Omni to extract entities from context we're passing. We pass in the text, we pass in the LLM client, and now we can generate an extraction of entities from the content we pass in. We usually have the name, type, and a description of the entity. The instruction for this entity summary, which you can look at as prompt engineering, is I'm telling the LLM to extract entities from the text. We want it to return in this format, which is the name, the type. It could be a person, place, or system. It can be a subject, an object, or place subject, and actually a system, which is artificial, and a description, which I want to be quite brief. You're going to see this in action very soon. We can write to entity, and we have all the operation as well. This is a summary as well. We're going to run this function and initialize our memory manager right here. We're going to call the memory manager class, passing the connection to our database, passing the conversation table, and the rest of the vector store we expect it to use. And that's it. We've initialized our memory manager. Now, I want to talk about the concept of an agent's toolbox, because one thing that agents need is to have extensive capabilities. The way we improve an agent's capability is by adding tools to the agent. Tools can be scripts that we've written. It could be REST APIs that we're connecting to. It could be MCPs as well that we're connecting to out there. Essentially, the reason why you need a toolbox is because the context window is limited. And whenever you pass in tool information, which is in the form of a JSON schema object, whenever you pass this into the context window, if you have a large amount of tools, you are going to exceed that context window length. Tool selection is very important. When you give a large number of tools to an LLM, it can cause confusion, especially when tools are similarly named. The LLM can distinguish one tool from another, and it causes it to call the wrong tool. So there's some problems that this agent toolbox solves: context bloat, tool selection failure, increased latency, again, more tokens, slower inference, and higher operational costs. So what is this toolbox? It's very simple. Whenever we have a function within our system, we ingest that into the database. When we ingest it, we create embeddings with the information of the function that we want our agents to have awareness of. This embedding allows us to use a vector search retrieval method just before inference to only retrieve tools that are semantically similar to whatever instruction or prompts or query that is being passed in at that specific time. As opposed to passing in 100 tools, you only pass in maybe 3 tools that you require for that specific query. We're going to see this in action. I've kept some instruction on how this works. We have different components for the toolbox, but one thing I want to bring your attention to is a bit of memory engineering. I augment the information that we actually pass into the database related to the tool itself. For example, I augment the docstring using an LLM. Sometimes you might write sparse docstrings, or docstrings are not detailed, and this doesn't help the LLM to select the right tools. So you can actually use an LLM to augment the docstring as well to add more information. But also you can use an LLM to generate example queries that can trigger specific tools. Or you can fill this in yourself if you know the type of queries you expect. Within this metadata information in your database that corresponds to your tool, you can conduct hybrid search, right? Where you use semantic similarity and keyword search to retrieve the right tool. Or you can have a richer embedding that captures more information relating to the tools and when they should be used, which improves your semantic retrieval as well. So I've kept in some examples here. With memory engineering, we're using Toolbox as procedural. Retrieval can be seen as context engineering. Context offloading is also context engineering. Role setting or role playing is prompt engineering as well. So we're seeing that there is this intersection within all the engineering disciplines when it comes to agent engineering. The way I've implemented the Toolbox feature is whenever you put this decorator on top of a function, you can either choose to augment it or not. Augment true, it will mean that it uses an LLM to augment the docstring and generates the example queries. This is the actual toolbox itself. We have this get embedding function, which we're going to use later, which just uses the Hugging Face embedding that we initialized earlier. Now we have this tool metadata. This is a data model for the actual tool. We have the name, description, signature, parameters, and the return types. This is the class of the toolbox. Whenever you initialize a toolbox, we have the memory manager, the LLM client, a model itself, and tools by name. The function augment docstring, I already said what it does, but very quickly, what we're doing is very simple. We pass a prompt that tells the LLM to generate a detailed description of what the function does. And we're passing the docstring of the function itself. We only return the improved docstring and no other text. We expect it to do the appropriate thing. And then for generating queries, again, a simple prompt. Basically, we're saying based on the following tool description, generate 5 or so queries and return those in a list to us. And again, this is what we're doing when we're using LLMs for actually augmenting some of the tool information here, just to improve semantic retrieval and retrieval strategies. So the rest of this goes into some detail as to how we're building this toolbox. I'm just going to run this cell and we should be good. Now we're going to initialize our OpenAI client and we're going to actually initialize our toolbox as well. You're going to need an OpenAI key for this, so make sure you have it. Let's look into context engineering. In this notebook, we talk about context engineering. We've already touched on it a bit and we're going to go into detail. For any form of context engineering technique, you need to understand how your context window is being used. When I say you, I mean you as the engineer, and also your LLM needs to understand how much room they have for the context window. And you're going to see a lot of tools like Cursor and other tools that have awareness of the amount of context window left, the amount of tokens left to use within the context window. We implemented this within this system and given our LLM awareness of this context window utilization. Summarization is a context engineering technique, and we can offload a summary to memory, which is also a context engineering technique. Just-in-time retrieval is a retrieval step used within context engineering. Whenever we do a summary, we want to keep a placeholder of the summary within the context window. We keep the summary ID with a very brief description of the summary. When we're in the agent loop doing an execution, when the LLM sees that it might need to use a summary, it can just use the expand summary tool, which would have the ID of the summary, to then uncompress a certain summary to get more information. So this again is agentic, and the agent can basically use this tool whenever it needs to. Just-in-time retrieval, and we're retrieving information just when we need it, as opposed to generating vector embeddings and doing some pre-computation. All right, so these are just the functions calculated the context window usage. For the summarized context window, this is how it's basically structured. We're going to be using an LLM to summarize the context window. We're just saying summarize this particular content, which is truncated in 2 to 3 sentences, right? Again, you can do something more extensive. You can do a bit of prompt engineering and tell the LLM what to summarize or what to pay certain attention to. You want to pay attention to emotional information in a specific context, and that should be the anchor for the summary, right? So the different ways you can summarize, and it's beyond the scope of this notebook to actually talk about it, but we can look at different techniques in the future. And now we're creating a description for the summary. Remember, I said we put the description in the placeholder within the context window. And this is the offload summary. That's a bad naming, but this basically is the context offloader, where we take a summary and we actually offload the context to summary. We summarize the context window and then we pass that into the actual database. The LLM can do that because we have this memory manager. which has the summary memory. In the memory manager, we write the content and the summary. There are different ways you can implement this. You can remove the content and just look at the conversation IDs or the thread ID you've used to generate the summary to reconstruct the uncompressed summary version. But here I'm just storing the full content and the summarized as well. We're gonna run this cell. And now we have the summary tools and conversation compaction. We're gonna make this tools for the agent. So expand summary, we have a memory manager. We're gonna be able to read the summary, which means the agents can just pass in the summary ID placed in the context window to expand the summary. This is just-in-time retrieval, very simple. And then we have this summarize and store. So the agents can actually summarize the content within a context window and store that in memory using this specific function. Again, we're going to store that into our toolbox memory as well. Those are the two tools that our agents can access. We're going to run this. It might take a while because we're augmenting them as well. We're going to extend this doc string and generate some queries that we're going to pass into the metadata of this tools as well. While that is running, I'm going to talk about how we're able to get more context for our specific LLM or agent by going over to the internet. We're going to be using Tavily to conduct internet searching. Tavily is a tool that allows you to give your agents or LLM access to web data. I'm just be conducting a very simple search query using Tavily, and that gets information from the internet. But here is the trick. The information we get, I actually store that back into memory as well. I store that back into our Oracle AI database, and that is exactly what we're doing. So web access with Tavily. So you're going to need a Tavily API key. They have a free tier, so you get your API key and you can use it free and easily. So this is the functionality. We're going to use this function to search the web and store the results in the knowledge base. Whatever information we get from the web, we store that in the knowledge base table, which is some form of semantic memory. We call the Tavily client, we call the search method and pass in the query. We specify the max result that we actually want. We format the results because we're going to create this model of the actual results we get, including the URL, the title, the score obtained from Tavily. The source type is always going to be Tavily search. The query used to search for information and the timestamp. We're going to store that into the knowledge base as well. When we ingest into the knowledge base, we're going to be generating embeddings from the text here is the title, the content, and the URLs. Now we can go into the agent execution. There are different components to this agent execution where we have the system prompt, and we are going to be able to execute tools and call the agent itself. This is where you get a bit of prompt engineering. So we're going into a bit of role playing, telling it it's an intelligent assistant where it has access to memory and tools. Also telling it about the type of memory it has. We're giving it some instruction on how it should answer queries. This LLM is going to be able to execute tools, and this is just basically giving that functionality for it to call tools by passing arguments and call tools within the toolbox by the name and the arguments decided to pass. Then we can call the OpenAI chat, passing different instructions and get a response back. An agent loop is a single iteration of an LLM that has an instruction and is able to achieve the objective of the instruction. There could be several loops involved depending on the amount of times it takes for the agent to achieve the task. There is a max iteration that is set here. You don't want to keep your agents running for an extended period of time, which can increase operational cost. In the agent loop, we're going to build context. That's the first thing, right? Context composition, organization is important. So we're going to build our context that we pass into the context window. I check the context usage. Whenever the context usage is above 80%, the agent is instructed to summarize and offload. I will do that programmatically myself, but also the agent can do that as well when it sees that it's 80%. Whenever we enter an agent loop, we're going to retrieve the tools that are relevant for that specific loop. And the way we do that is by passing in the specific query within that loop to retrieve some of the tools that correspond to it. Then we can store the user message in every execution. We're writing the user message and we're extracting entities as well. Within the agent loop for a certain number of iteration, we're going to go to the LLM, call the LLM, pass in the context and tools. If there are tool calls, we'll execute the tools, add the result to the existing message, pass into the database. And then if there are no tool calls, we're just going to return the final answer and then we save the results. Saving results means we write to workflow, extract entities from the response or the context itself, and restore the assistant response in conversational memory. These are the designs that go into context engineering. In the context loop, we're going to call it call agent and put in the max iteration. The default is 10. And we're going to pass in a thread ID. If no thread ID is passed in, we're going to default to 1. The query we pass in is the string entered by the user. We have our thread ID. We're going to set our thread ID. We have the number of steps. We have a list that is going to capture the steps we've taken. This is for workflow memory. And this is the tracked summaries as well. So the first one we're going to do is we're going to build a context from memory. Again, we're going to build a context from memory. We have the question that has been asked, and that's the query. Then we're going to add the conversational memory, the knowledge base, the workflow and read entity to passing in the query to make sure we're getting the right information. We're using semantic search for each of these memory types, right? We're getting the right memory that corresponds to the query being passed in. Therefore, we're only generating relevant context. We're optimizing each token to be relevant to the query and the problem domain. This is like an overlap of all of the engineering disciplines into one. Now we can visualize the context window by printing it out. Like I said, if we want to summarize a context, do this programmatically, but the agent itself can decide to do this as well because it's going to have awareness of the token usage. Here we're retrieving tools dynamically as well by passing in the query, and we just call the real toolbox, and we're only going to use the tools that we need for this query. Now, this read toolbox is not really optimized, right? There are ways you can optimize it. We can reduce the number of tools to just one. We can say we only want the agent to get the topmost tool that is relevant to this specific query, right? Or you can say, get me 3, right? There are ways you can optimize this specific toolbox retrieval strategy using vector search through the LangChain Oracle integration. Now we're going to write a conversational memory. We're storing the user conversation in here, and we are passing in the thread ID as well. And now we can go into the agent loop where we're able to pass in the system instruction that we have in the system prompt, and then we can pass in the actual context. Next, you can see we're starting within the agent loop. What we're doing here is we're actually going into, for the maximum number of iteration, we're actually just going to make a call to OpenAI, pass in the message and all the tools we want to use for the specific calls. This could be empty if there is no tools to be used as well. When we get the response, we're able to extract information from the response that could be the message itself. But if we see there's a tool call, we can call the tool and append that to the message. We get the name of the tool, get the argument, and call the tool using that execute tool function, the tool name and the argument. We see the results, print the results, and append the results to the message that can then get passed to the agent for the next iteration. If we go into a final answer, we print out our final answer and say we're done. Then we save all the information. We write the workflow, capture the query and steps in the final answer. We capture any entities we've seen. We write to the conversational memory the final answer from the assistant. We also track it using the specific thread ID. And that's the agent loop. So let's run this cell and try out our agent. I'm going to ask our agent, hi there, my name is Richmond. I am an AI developer. You can see it's trying to build a context. Let's see what's coming out. Hi there, my name is Richmond and I am an AI developer. This is the question. And here we can see the conversation memory is empty. We can see the knowledge base memory is empty. And there is no workflow, no retrieval, nothing. We can see context awareness of the tools the agent has access to for this specific time. There's an error here. I didn't actually initialize this agent system, so I'm just going to do that again. Okay, let's run that again. So we're just going to start using our agent, right? Our agent that has memory. Hi there, my name is Richmond. I am an AI developer. Just so you know, I'm running this again. Hi there, my name is Richmond. I'm an AI developer. And here you can see it has this awareness of the first time we asked it, again, because we had to rerun this. But we're using the same thread ID, so it remembers the conversation. Now, there is no memory as well. There is no relevant information in terms of workflow found. But here you can see the entity memory is working, right? You can see that it knows I'm Richmond and I'm an AI developer, which is pretty cool. It didn't have to make any tool calls. So saying, hi, Richmond, it's great to meet you. as an AI developer, what specific topics or questions do you have in mind? Now you can see entity memory has this awareness of an entity, which is me as Richmond. So let's just maybe look at using some tools. Hi there, my name is Richmond, I'm an AI developer. So let's ask it, can you get me the latest news in the AI space? The search gives it access to the internet. Conversational memory has all the conversation we've had before. There is no knowledge-based information here. There is no workflow here. And here we can see, what is it going to do? It notices Richmond AI developer multiple times and a person being addressed in this conversation. This is where you can go into memory engineering. We can start to optimize this memory manager to avoid duplicate entities and capture better information. But again, this is all memory engineering. You can see here in the first loop, it actually has 2 iterations. And the first loop is decided to use the Tavily search Tavily tool, right? It's passed in latest news in AI into the tool and it's gotten 5 results. And this is the results over here. It's just an internet search. Then in the second iteration, it's going to get the result from the tool call to construct the answer back to the user. It's able to give us this output. Here are some latest news sources in AI space, and these are all the news. I'm just going to ask it to do something here. Maybe this is the last question. Can you double click into the first news result and tell me more about it? Here you can see, now what I'm expecting to do is go into the first news result and get more information. But you can see the context is building up, right? You can see there's information here that is currently getting built up. Conversation memory is getting built up. Here we can see conversation memory is getting built up from the previous response. The first one, news, is NBC. I expected to get more information on this. You can see the entity memory is getting built up. We're getting some knowledge-based memory, getting some titles, it's getting some AI news. He's getting some information within his knowledge base memory. So as we're doing the internet search, we're updating the knowledge base as well. You split between searching the internet or going into the knowledge base whenever you are conducting an information search, where you tell the LLM to use the knowledge base, to check the knowledge base first before going to the internet search. In the first iteration, we have it go into latest news for AI. But it didn't need to do this because it was in that conversational history as well. We need some prompt engineering to tell it to use its knowledge. Then we try to expand a summary, but there were no summary. I don't know why it's doing that, trying to expand it. Then in the third iteration, it just passed in the entire context and it sees that I actually have the information I need already. I don't even need to do all of this tool calls. Again, context engineering, memory engineering, this is where you try to optimize your system and make it better. You can see that it knows the first news result was from NBC News. And one thing I forgot to show is workflow memory. Can you get me the latest news in the AI space? And you can see that it continued with the steps. In step 1, it was a success. And here is the answer, right? And that's workflow memory. The context window is getting utilized. And that's it, right? We're using different forms of memory. And this is showing that memory engineering is all about continuation, but it involves context engineering and prompt engineering, which are both maximization and optimization engineering disciplines. So I hope I've been able to show you how you can really evolve the way you engineer systems, giving you the foundation to actually build upon the techniques we've introduced here. There's so many things I've not shown, but this is just the beginning. For those of you interested in learning more about context engineering, memory engineering, you can go into the Oracle AI Developer Hub. I'll put the link in the description and comments below. Watch, fork this repository, because we're going to keep updating it and passing more information in. For example, in this notebook, in this repository, you can see how we do evals with RAG, and we've got a notebook that takes it from 0 to hero with building an agent from scratch without going through a bunch of abstractions as well. So we go into details and we're going to keep putting more content within this notebook as well. So see you in the next video.